Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will introduce complex numbers. Now you probably already know if you put into your calculator something like square root of -1, you will get an error. That's because this is not a real number. Real numbers are just the numbers you've been using up until now. It's all the rational and all the irrational numbers. You can't square any of those numbers to get -1. Now this has caused a lot of problems in mathematics. So luckily somebody came up with the idea to create the square root of -1. They called it I. So I is an imaginary number. It's not a real number. We just define I as the number that when you square it, you get an answer of -1. Now this is very useful in mathematics because it allows us to square root all negative numbers. So for example, something like the square root of -36, we can use our rules for surds. This is the square root of -1 times the square root of 36. Of course, square root of -1 is just I, square root of 36 is 6. This is the number 6i. Similarly, if you want to square root a number like -2, it's just root 2i. So these numbers, I, 6i, root 2i, are imaginary numbers. They allow us to get around the problem whereby we couldn't previously square root negative numbers. And remember that had a lot of implications. For example, when we were solving quadratics, if the quadratic had a negative discriminant, we couldn't find any real solutions. And we'll see later in this course that now we actually can always find solutions to quadratic equations. So complex numbers have very many uses across mathematics. So what exactly is a complex number? Well, a complex number Z is a number of the form A plus IB. So here, A and B are real numbers. They're like the numbers you know. Could be 2, 3, square root of 5, whatever. So these two are real numbers, but I is imaginary. So Z, a complex number, has basically a real and an imaginary part. So REZ means the real part of Z, it's just whatever A is, and the imaginary part of Z is whatever B is. It's whatever the number is that is attached to I. So it turns out that all real numbers are complex numbers, but not all complex numbers are real numbers. We write this mathematically as real numbers are a subset of complex numbers. But complex numbers has far more than just the real numbers. It has real numbers like 4, root 5, whatever. It also has purely imaginary numbers like 6i, and it has other complex numbers that have a real part and an imaginary part. So we can think of real numbers kind of like we thought of vectors. So let's say, for example, we have z equals 3 minus 4i. This is an example of a complex number. So we can plot it in the plane. Now we don't use the same Cartesian plane that we use for vectors. We use this Argand plane. So it has an imaginary axis, that's the vertical axis, and a real axis, that's the horizontal axis. So if I want to plot 3 minus 4i, I just plot 3 on the real axis. The real part of this number is 3. The imaginary part is -4, so I go down here and plot -4. So we can think of 3 minus 4i as a vector from the origin to this point 3, -4. So just be careful here, because when we were doing vectors, remember I was the x component, but here it's the vertical component because that's the imaginary part of the number. So just make sure you're aware of that. Now, because we can treat z like a vector, complex numbers like a vector, we can do a few calculations similar to what we did for vectors. So if I want to calculate this is the magnitude or size of z, I do it the same way I would for vectors. I just use Pythagoras. It's the square root of the sum of the squares of each component. It'll just be the square root of 3 squared plus 4 squared, which is 5. So this allows us to compare or get some measure of the size of complex numbers. So z has magnitude 5. So just as we did for vectors, we can multiply complex numbers by a scalar. So let's say, for example, I'm going to multiply z by 2. I just multiply each component by 2. I multiply the real component by 2. 3 times 2 is 6. And multiply the imaginary part by 2. Negative 4 times 2 is negative 8. Now we can multiply z by the number I. So I just multiply 3 by I, that's fine. But then I have to take negative 4i and times it by I. So what would this be here? Well, I times I is I squared, which is negative 1. This is 3i minus 4 times negative 1. So it's actually 3i plus 4. So just as we did for vectors, we can write complex numbers in polar form. But the polar form we use for complex numbers is r cis theta. Now, r has the same meaning. It's the magnitude of the complex number, which we calculated as 5, and theta has the same meaning. It is the tan inverse of the y component, in this case the imaginary component, over the x component. So if you put tan inverse of negative 4 over 3 on your calculator, you get negative 53 or thereabouts. So this angle here is 53 degrees. Remember, negative means it's going clockwise rather than anti-clockwise. But of course, the angle that we report is the angle made with the positive x-axis going anti-clockwise. So this angle here will be 360 minus 53. It'll be 307 degrees. So in our polar form, this will be 5 cis 307 degrees. Now this cis has a slightly different meaning. It stands for cos I sine. So what that means is z is 5 cos 307 plus I sine 307, because sine gives us the imaginary component. Now this form, as we will see, is very, very important. It allows us to calculate powers of complex numbers very efficiently. So I said before z equals 3 minus 4i, let's introduce another complex number like w equals, for example, 2 plus I. Just as we did for vectors, we can add two complex numbers by simply adding the components separately. So we add together their real components, 3 plus 2 is equal to 5, and we add their imaginary components. Minus 4 plus 1 is minus 3. So z plus w is 5 minus 3i. Similarly, z minus w, we subtract the components. Real minus real, 3 minus 2 is 1, and then imaginary minus imaginary. Negative 4 minus 1 is negative 5. How easy is that? All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.